Hello again. It's time once again for more of Physics 142. In this video, I want to do more examples of using Faraday's law and Lenz's law and understanding the phenomena of magnetic induction. So just to review a little bit, we've been talking about magnetic induction, and the idea here is that if you change the magnetic flux through some loops, through some wire, you can induce a current in that wire. And so we wrote that down mathematically here as Faraday's law. We said if we take the time derivative of the flux, we look how the flux changes with time, that will induce an EMF, or a potential difference, in our circuit, which then, of course, can create current, right? EMF is I times R, V equals I R, so that will create some current. And we talked about the fact that there are three different ways that you can change the magnetic flux, right? So if we write this down, let's just go through this one more time. If we write this down, magnetic flux is this surface integral, right? You integrate over whatever surface you're dealing with, right? If you're, have some loop, the surface, right, is the surface enclosed by that loop, right? So you integrate over whatever surface of B, the magnetic field, dotted with the area, right? Remember, the area vector is a vector that's perpendicular to the surface, right? Those are area vectors, right? If you have some complicated surface, right, then you break it up into a bunch of little pieces, which are all little dAs, right? And then for each spot, right, you look at the magnetic field going through that spot, right? Whatever magnetic field you have going through that spot, and you take the dot product. Taking the dot product means minus d dt, the integral over the surface, where at each little spot in the surface, you're doing B times dA times the cosine of the angle between them, right? The magnitude of B, the amount of B going through that little chunk, times the amount of dA, right? That's just the area of that little chunk. And the dot product means you take the cosine of the angle between those two vectors, right? Now, if your surface is nice and uniform, right, if you have a nice uniform surface, and if you have uniform magnetic field coming through that surface, right, if the magnetic field is the same everywhere on that surface, then B and cosine theta can both come out of the integral, and you just end up adding up, integrating all the area vectors, right? This is an integral over area. So it doesn't cancel the ddt, it's an integral over area, just means add up all the area. And so if you have a nice, for nice surfaces with uniform field, right, for nice surfaces with uniform field, we just get that this is ddt minus ddt of B A cosine theta, right? And so what that means here is that there are really three different things that you can change, right? You could have a changing magnetic field, right? If area is constant and theta is constant and just the magnetic field is changing, then we have sort of three options here. Then the EMF could be minus dB dt, and then you just have times A times cosine theta, right? Or I could change the area, in which case this would be B minus B times dA dt, right? If the area is changing with time, times cosine theta, right? Or you could imagine changing the angle with time, right? Then I'd have the EMF is minus BA ddt of cosine theta, right? So really we could change any of those three things with time. And so in this video, I want to sort of do one more example of changing each of these, right? One example where each of these things is changing, just to really give you a sense of how changing magnetic flux is inducing a potential difference and therefore inducing a current. So let's start then with the following example. All right, so let's do three examples. All right, one each. And so the example I want to start with is I want to think about a current loop. All right, so here we'll have a current loop. All right, and in that current loop, I want to have some magnetic field going through it. All right, so I'll put some magnetic field going through the current loop. All right, so there's magnetic field. But so I got magnetic field all around, right? But here's the thing, I want to now take this loop, and it's not actually just straight perpendicular to magnetic field. I want to tilt it a little bit. All right, so this is sort of the end-on view. All right, if we take a side view, all right, so maybe I'm sitting over here, right? This would be my eye looking at it, right? If I take a side view, the magnetic field is going like this, away from my perspective, right, into the page, all right? And I want to take this current loop and I want to tilt it at 30 degrees with respect to the vertical here, all right? So I'm gonna tilt it at an angle of 30 degrees, all right? So that's a little different. So now we've tilted our wire loop with respect to the magnetic field. So that means the area vector, right? If I was to represent all of this area here, right? The area as a vector, the area vector would be coming out like this, right? And so this would be my 30-degree angle right there between B and the area vector, right? This is my area vector for that loop. So the question I want to ask, though, is let's suppose that we take this magnetic field now, all right? So we take B, all right? There's our magnetic field, and now we decrease it, all right? So let's decrease it, and to be concrete, let's decrease B at 0.2 Teslas per second, all right? So that's pretty fast, right? 0.2 Teslas per second. Going to decrease that magnetic field. And, you know, we really probably should put some dimensions on our other things. So we've got a 30-degree angle. Let's make our hoop have a radius, all right? A radius of 1 meter squared, all right? We'll have a 1 meter squared. I guess I should probably do some sig figs here. So 0.00 meters squared. All right, there we go. So we'll have a 1 meter square hoop, and we're going to decrease the magnetic field at 0.2 Teslas per second. And so the question is, what's the magnitude of our induced EMF? So what is the magnitude of the induced EMF? All right, and what is the direction of the induced current? All right, and what is the direction of the induced current? All right, I guess this is the induced EMF, right? And what's the direction of the induced current? So those are the questions that we need to figure out here. So how do we do it? Well, we go ahead and we use Faraday's law. And Faraday's law says that, well, that the induced EMF, right, is minus the time rate of change of the magnetic flux. And so that's going to be minus d dt. And now flux, remember, is this surface integral. We wrote it down up here, right? And this is a nice uniform surface where the magnetic field is uniform throughout that surface, right? It's the same strength throughout. And so I'm going to just go ahead and realize that we can integrate over that area and just write this as B times A times cosine of theta, all right? Because it's the same everywhere at all the spots in the hoop there, all right? And, well, now A is constant with time, right? A isn't changing with time. My loop isn't getting bigger or smaller. Theta is constant with time. I've tilted it, but I'm not spinning it. It's just tilted, so that can come out. And so I get minus B times cosine theta times dA. Wow, that was a real struggle. Let's try again. We just said A is constant. That comes out. Cosine theta, that comes out. And B isn't, right? So dB dt, that's the thing that is changing here, dB dt. Okay, So there we have it. We now have a formula that we can plug numbers into. All right, so let's go ahead and do that. So the area here, what's the area? Well, the area of my circle is pi times the radius, which is 1 meter squared, right? That's the area of my hoop. Now I need the cosine of the angle between B and A. Well, the angle between B and A, we already noted that. That's 30 degrees, all right? And then, well, what is dB dt? dB dt, that's the rate of change in the magnetic field, and we just said that's 0.2 Teslas per second, right? So we can plug in 0.2 Teslas per second, all right? That's our rate of change of the magnetic field, and I got to keep my minus sign around here, and so if you plug that all in, type that all together, I get minus 0.54 Tesla meters squared per second, right? Tesla per second times meters squared. That's the units. And now this is an EMF, right? And so an EMF, or that an EMF is a potential difference, a voltage, right? So I could also write this as minus 0.54 volts, where the minus sign is just, again, indicating the direction here, right? The minus sign is the direction. And just an interesting thing to point out, all right, that Faraday's law actually tells us an interesting units relationship, that 1 Tesla meter squared per second must be 1 volt, all right, that these things are the same. And so that's an interesting relationship to know about volts. All right, so this is all well and good. We have the magnitude, but what do we mean by this minus sign, right? What are we doing with that direction? What is the direction of the induced current? Well, how are we going to figure that out? Well, we know from Lenz's law that the current needs to oppose the change, right? It needs to induce a magnetic field that opposes the change. So, well, let's think about what's going on here. So, if our magnetic field is decreasing, right? Our magnetic field is decreasing. So the magnetic field is this way, right? Right? That's the direction of our magnetic field, but it's decreasing, right? So if it's decreasing, that means the decrease, or delta B, is going to be this way, right? That if it's decreasing, that's opposite the field. And so we need our induced field then, right? B induced. And maybe I'll do that in green, just to make sure the induced has a different color, right? So if the change is to the left, right, then the induced needs to be to the right, right? And, well, you know, okay, so now it's tilted at an angle, right? The current can only flow actually in the loop, right? So let's think about, if I need to create some magnetic field that is mostly this way in this loop, how am I going to do it? Well, I need magnetic field coming out of the loop this way. I put my thumb, the direction I need the magnetic field to go. I curl my fingers. That will tell me the direction of the current. So what that indicates to me from this is that if I'm inducing a magnetic field here to the right, then the current at the top will be flowing out of the page, and the current at the bottom, the induced current at the bottom, will be flowing into the page, right? And so what does that look like here from sort of this perspective, right? If you're looking at it from this side, well, that would look like clockwise current there, all right? So the direction then would be clockwise current. All right, so again, right, the magnetic field here was into the page or to the right, but then it's decreasing, right? And so that means that the induced field must also be to the right, right? Because you need to oppose that drop-off. All right, good. So that's an example where we have changing dB dt, all right? But perhaps even more interesting example is, what if instead I change something like the angle? All right, so I want to take this setup and have a similar setup. All right, so for example number 2 here, all right, hey, I'll get a little bit more board space here to do the next example. All right, so for example number 2, let's keep a sort of a similar setup. All right, so here's my loop again. All right, but now I'm going to take and I'm going to attach this loop to some axle. All right, and well, we'll still have, I guess before I do that, we're still going to have magnetic field here. All right, so we'll still send some magnetic field through it. All right, so there it goes. I've just, you know, it can be magnetic field wherever, right? It creates some magnetic field. All right, lots of magnetic field. We get the idea. I should probably make it uniform. So can imagine that this is a uniform magnetic field. Maybe if I erase a couple of those, that make it look. Let's just redraw that. Goodness gracious. Let's make a uniform looking magnetic field. So here's my hoop. All right, and here is my uniform magnetic field. All right, there we go. Okay, now let's take and attach this hoop to some sort of axle that I can spin. All right, so and I can spin it maybe at some rate, at a rate omega. So, you know, you can imagine, right, this bottom part is going to come up out of the page and the top part will go into the page, right? So I can take this hoop and spin it now, right? So just like I tilted it here, now I'm tilting it, but now I actually want to spin it. And I want to keep the magnetic field constant now, right? So now we're going to have the magnetic field be a constant 1 Tesla. All right, so we'll just keep that magnetic field constant. And, excuse me, almost had a sneeze. Oh, guess not. All right. So, you know, how am I spinning this? Well, you could imagine, you know, you could hook this up to a piston. You could hook this up to like a wind turbine that spins this, right? You could hook this up to, you know, some sort of, you know, anything that rotates, a mill in a river or whatever, right? Anything, a gas engine, right? Anything that gets this to spin, right? And the goal is we want to induce some current in this loop that then maybe could, you know, go out and power something, right? So what this is going to do is this is actually a setup that will create sort of a generator where we'll use mechanical motion, we'll use the spinning motion to generate some current. So let's see if we can see how that works, all right? So let's suppose I'm going to rotate this at a rate of 1 hertz, all right? So we'll just rotate it 1 time a second to start. And the question is, again, what is the induced EMF and what's the direction of the current? And I guess the direction, well, we'll see. But let's first think about the induced EMF. So how do we do that? Well, again, we write down that the induced EMF is minus d phi dt, right? And again, we have a nice uniform area where the magnetic field is uniform all over that area. All right, so that means that when I do minus ddt of the integral of b dA cosine theta, all right, the b and the theta are constant with area, and so we can just write this as minus ddt of b times a times cosine of theta. All right, so that's all well and good. But now let's think about what's changing. Well, my magnetic field, that's constant. That's a Tesla. All right, my area, if we just assume that, again, this has a radius r of 1 meter, all right, we'll assume this is a radius of 1 meter. My area is also not changing with time. So both of those come out, and the only thing that's changing now is the angle between the B field and the hoop, right? If you sort of looked at this from the side again, right? If we looked at this from the side, as this thing spins, right, it starts like this, and then it's going to be like this, and then it's going to be like this, right? And so that area vector is going to be continuing to spin, right? And so it's the angle between B and A here is going to be constantly changing. So let's write that down. So now we have B minus B times A times ddt of cosine theta. So cosine theta is the part that's changing. And now, well, what do we do with this, right? How do I take a time derivative of cosine theta? How do I relate that to omega here, all right? Well, now we have to harken back briefly to just a little bit of physics 141 and remember the relationship between angles, right? Angles and angular frequency, right? And what is that relationship? Well, you might recall that delta theta, changes in theta, right? Delta theta over delta time is omega, right? Or another way we could write that is that theta is theta naught plus omega times t, right? If we multiply over by the t, right? Usually we just say we start at an angle of 0 degrees, right? Or I guess I should say 0 radians, right? 0 radians. What we're going to get is that theta is omega times time, right? And it's just like distance is velocity times time, except for angles. The angle theta you rotate through is your angular frequency times time, right? Radians per second times time will give you radians. So for theta, I can just plug in omega t. So let's go ahead and do that. And this is good because I'm trying to take a derivative with respect to time. It would be good to have an actual time thing in here that I can actually take a derivative, right? So I need to actually have a t that I can take the derivative with. So let's do that. So this is going to be minus b times a times d dt of cosine of omega t. And yeah, isn't this fun? Bringing back all the Physics 141 memories here. All right, we've got a cosine of omega t. And well, now we can take the derivative of this. We know how to take the derivative of cosine omega t. We did that earlier in this semester, right? Taking the derivative of cosine, well, derivative of cosine is going to give us a sine, right? And we're going to get an omega that comes out front and a minus sign, right? So this will turn into b times a times omega times sine of omega t, right? So that's what happens when we take that derivative. And, well, what does this mean? All right. Well, this means that the EMF that's getting induced is actually going to change as time passes, right? So if we actually plugged in some numbers, so let's do that. Let's plug in some numbers. So B would be 1 Tesla, and our area is going to be pi times 1 meter squared, all right? Omega, that's 1 hertz, and 1 hertz, well, how does that, well, 1 hertz is actually the frequency. So I should be careful. This isn't, omega is radians per second. Hertz is just cycles per second. So I have to multiply that by 2 pi, right? It's just, I'll just note this here, right? Remember, omega is 2 pi times frequency, cycles per second to radians per second. We need to factor a 2 pi. So omega means we go through 2 pi radians every 1 second, right? That's what 1 hertz means, okay? So we plug in for omega, and then we just have this sine of 2 pi times t, right? Where 2 pi again is omega. And so what we get is sine is something that's going to cycle back and forth between +1 and -1, right? So the sine will cycle back and forth between +1 and -1. This is going to be, looks like 2 pi squared, right? So, you know, I'll go for 2 pi squared, which is about 20, right? About 20 volts. And but it oscillates, right? So this is the max, right? The max induced EMF. But then it's going to oscillate back and forth between 20 volts and -20 volts, right? Because sine is going to go between +1 and -1. Sometimes it'll be 0, sometimes it'll be -20, sometimes it'll be +20. And so what we've done here, by taking like a wind turbine or any other kind of turbine, something that makes this axis spin, and spinning a loop in the magnetic field, when we spin this loop in the magnetic field, what happens is we generate an alternating current, right? We're going to generate, well, first it's going to go one way, right? 20 volts that will give us a current one direction, right? But then the sign will change and we'll get current the other direction. So we'll get current one way, then current the other way, then current one way, then current the other way. And so this is how we generate alternating current. How generators work is you take a current loop, you spin it in a magnetic field, and voila, you have created an AC current generator. So I think that's pretty cool. I have one more example of another where we're actually changing the area. This video is getting a little long, so I'll do that in one more in the next video. Thanks.